Hey guys, this is Saptashi here and welcome to our YouTube channel. Last video tutorial we have discussed about CNN and we have understood that visual cortex, the part of the brain which is actually responsible for human vision, has motivated the architecture of CNN in very many ways. Couple of building blocks which are different from traditional ANN is the convolution block and the pooling block or the subsampling. In today's lecture or today's tutorial, we'll focus on this convolution operation. Okay. Let's do a quick recap of how CNN works. So it is an image classification task, the example that you see over here. So I have an image which is given as a 28 into 28 matrix, right? Small elements of the matrix is called as picture element or pixel. So it is actually 28 into 28 pixel image. So this is the input, and what is the expected output? The output is that you should be able to classify this as 5. Okay, the label of the image is 5, and this can actually be bifurcated in two principal areas. So one area is called as the feature extraction area. So this convolution layer, then the pooling layer, again convolution layer, pooling layer. So this is your feature extraction layer, and then you have the classification layer. Okay. In the classification layer, traditional artificial neural net is used, and that is what happens in a conventional CNN. However, you are free to use any other classifiers like support vector machine, random forest, etc. on this feature extraction layers. Okay. One other thing that I want you to pay attention is that this metric size as you go through the layers actually gets reduced, right? And uh, the number of such matrices, so you only have one 2D matrix as input, but as you go through the layers, the number of 2D matrices increase, right? So these are a couple of properties of CNN which happens because of this convolution operations, right? Now let's take a closer look to the convolution operation. Okay, so let's say you have an input signal given as AX, and you have a convolution operator which is typically represented by asterisk, okay, and you have a filter F. So once you apply this filter on AX, basically you get your target or your output. Okay, so that is how your convolution operation occurs. Now, X and F need to be compatible. So if X is a 1D, 1D array, F also needs to be a 1D array. If X is 2D, F also needs to be 2D, and so on and so forth. So here, if you look at this image, this is your X, okay, this is your F, all right, and this is your Y, all right. Now, what is happening is that you are doing an element-wise operation, but please see that F is of a smaller dimension. It is a 3 by 3 matrix, and X is a 7 by 7 matrix. So how do I do an element-wise operation? So what I will do is I will take this and start putting it from the top left corner. So I'll select a 3 by 3 matrix from the top left corner like this. Okay, like this I will select a 3 by 3 matrix. Then what we'll do is I will simply do an element wise multiplication. So 0 will be multiplied by 4. This 0 will be multiplied by 0. This 0 will be multiplied by 0. 1 will be multiplied by 0. 2 will be multiplied by minus 4, and so on and so forth. So if you do this multiplication and add it up, then you will get a value of minus 8. So this is what needs to go to the target, and where it will go in the target. So it will correspond to the central pixel. So as a result, the dimension of this target, image or target matrix will be smaller than the source image. Okay. Now this is about the first pixel calculation. Then what you can do is you can slide little bit, and you can pick the next 3 by 3 matrix like this. Okay. Again, we will do element wise multiplication, and then sum it up, and we'll get some value for this. Okay, and that's how it will proceed. And actually, here we have just taken a stride of 1 pixel, right, which is called as stride of 1. I could have also taken stride of 2, started from this 0, right. I could have started from here, I could have started from here. So it depends on what stride I am taking, and based on that, actually your target size also will be reduced. Now let's try to understand the connection between convolution and image classification. So let's go to our traditional machine learning. In traditional machine learning, there were different algorithms, okay, different algorithms which are applied on the images. Images still represented as a 2D matrix. Those algorithms will extract certain characteristics of the images. As example, it can extract the edges. As example, it can extract the texture. It can extract the color histogram, and so on and so forth, right? And so, if this is an input image, if you apply an edge detection algorithm, then you will get a result like this. So this was one of the motivations that a machine learning algorithm wanted to find out different features of the image which helps in the image classification. Now, what's the connection of this finding of features with the convolution or filters that we discussed? So let's say we have a 2D matrix like this. So the center pixel you see are of higher intensity or brighter intensity, and those at the corner has 0 intensity value, right? So the value can be between 0 to 255 if we are taking a grayscale, and roughly we can think that our image will be something like this, right? So what we want to do over here is we want to identify the vertical edges. How many vertical edges are here? So one vertical edge is over here and another vertical edge is over here. So that's what we want to actually find out. And actually, how can we find this out? So basically, you can think of that where there is a change in intensity, right? A drastic change in intensity, then there is an edge. Okay. So this is what is happening over here. This is what is happening over here. And you see there is no change in the intensity over here. So there, of course, there is no edge, right? And you can think of finding this out by using derivatives, right? And these derivatives can be calculated using the differences. So let's say I want to find derivative at this point. Let's say this is point x2, right? And if this point is x1 and this point is x3, then actually x1 minus x3 gives you an idea about the derivative, right? Idea about the derivative. So this is about 1.1 pixel, but if I want to apply it for a patch, right? So what I can do is I can actually use a matrix, something like this, and see what this is doing. So it is basically doing this into 1, which is for this x1, and then it is not considering the middle pixels, as we have not used the middle pixel, and finally we have used these pixels and did a -1. So basically I am getting x1 minus x3 in one shot, right? And the idea is that you apply like this, as we have discussed earlier. So you pick a 3 by 3 portion, right? You pick a 3 by 3 portion which is same as your filter size, and then you slide and take it through the entire image. Okay, and if you do that, then you get a matrix like this, and it clearly tells you that there are 2 vertical edges over here, right? Lot of changes happening, and there are no changes in between, and then finally you have changes over here. Okay, so as I explained earlier also, that you see here, as you see that the target image is of smaller size than the source image. So this is one of the issues that we try to handle later on using padding. All right. So we have understood, or we can generalize, that filter is a kind of square matrix which can be 3 by 3, 5 by 5, or 7 by 7, which has parameters or values like w1, w2, w3. So these were the ones, so w1, w2, w3 were 1, 1, 1, in case of vertical edge detected, right? Similarly, you can see different filters with different weight values, right? So in traditional machine learning algorithm, what we'll do is you will have your images, and you will have this kind of filters applied on this, and we'll get the features, right? So these filters are also called as kernels, also called as feature detector. And when a feature detector is applied on an input image, you get a feature map. So if you have multiple filters, you will get multiple feature maps, right? So that's how you had one image as an input, but your number of images were getting exploded because of number of filters or number of kernels that were getting used, right? And stride is your steps in input image, which we have already discussed. So as we were trying to tell that traditional machine learning would try to find out such filters, okay, try to find out such filters which are best for the task at hand, right? And there are plethora of filters, right? So it converged or it converted to a trial and error problem where you will pick different filters, extract different features, and then classify on them, right? So in deep learning, what happens is that these filters become learnable. So you remember that the network parameters in a traditional ANN can be learned through your gradient descent and back propagation by use of your loss function, right? Same thing will happen here. So these filter weights are also now parameters of the convolutional neural net. So what is happening is that you do not need to do this, handcrafted feature extraction, but automatically based filters will be learned for your image, right? And couple of things where this is different from your traditional ANNs, that it applies on a local area, right? Not on the entire image at the same time, right? So giving you the idea of local receptor field of your visual cortex. So that thing you call as sparse connectivity, because earlier if you have if you have a 10,000 size pixel, right? 10,000 size image, okay, it is flattened, then you need 10,000 parameters. But here that is not what is happening. So only nine parameters are getting applied. So it's not a dense connectivity but a sparse connectivity. Also, there is one important thing which is parameter sharing. So these same filter parameters or these same filter weights are going to be applied on the entire image by sliding, right? So these are key characteristics which makes CNN more efficient than your traditional ANN. All right. Okay. And the convolutional layer is a nonlinear layer and pooling is a linear layer. So convolution is a nonlinear layer because it uses ReLU. And as you remember from our activation function discussion, ReLU simply makes the negative value 0. So if you have an input like this to ReLU, then this minus 110 has been converted to 0, and that's all ReLU does. Now let's go and look at padding. Okay, so the basic idea is that if you have an input image like this which has its height and width. So let's say this is h1, okay, and this is w1, right? So when you apply your filters, then your image size will be h2 and w2, right? Of course, you can understand that H2 will be smaller than H1, and W2 will be smaller than W2. W1 will be greater than W2, right? So as a result, as you move from layer to layer, your images become quite small. That is number one problem. Second problem is the information around the border gets lost, right? Because it goes to the central pixel. So to handle that, what you often do is you increase the size of this image. Okay, you increase the size of this image and you can put zero values over here. So once you increase this size of the image, this is called as padding. And when you put zero across all the increased pixel, that is called as zero padding. And one of the objectives, one of the schemes can be that you increase your padding in such a way so that your input image and output image is of the same size. That option is called as same padding. And if you don't apply any padding, no padding, right, then your target image is smaller, and then you call it as a valid padding. Okay, so where your image size gets reduced. Now these two equations that you see over here, so I already explained about W1 and H1, right? I also explained about W2 and H2. Now there are a couple of more things. One is the size of the filter, right? So filter size is given as FH and FW, and also the strides that you are taking, which are taken as SW and SH. So P is actually what you want to determine is P. So P actually tells you from this equation that how much padding you should apply so that your source image has same dimension as target image, right? And you see that W2 and H2 has symmetric equation because they apply in similar manner. So let's understand this further with an example. So let's say this green marked portion, right? This 5 by 5 matrix in the middle, right? Uh, this is what is your source image, and then you have applied this filter, and you want to get this target mapping. So that they are of same size, what you have done is you have zero padded this, okay? And here actually value of P is 1, right? So you have padded 1 pixel here and padded 1 pixel here. So both sides you have PP, total 2P, okay? Now if I go to this equation, what I want is I want W2 to be same as W1, isn't it? And in our case, let's assume SW is 1. So in that case, what happens is, this equation turns out to be minus FW plus 2P, right? Plus 2P plus 1, this is equal to 0. Okay. And what is your FW? What is your FW? FW is 3. So actually your 2P becomes 2, okay, and your P becomes 1. So that's how you come to know that if you pad by one column both sides, then you will get same padding, right, or same size targeting. Okay, so that brings us to the closer of this lecture. Okay, thanks guys for watching this video tutorial. And as every time, if you have liked this, please give your comments, like and subscribe. Okay, thanks a lot guys.